Hello, I'm Andrew Portelis, and this is Project 2 A-Star Pathfinding for CS-611 Game AI with Professor Essen. As you can see, the character moves around correctly using A-Star, and if we go down to the enemy, we can see that they are rapidly moving around and quickly overtaking my character. To make this A-Star work, I started out with a A-Star node which has the x and y coordinates for the location in the grid of the game, a g value, which is the step away from the starting node as we run through the A-star algorithm, and h is the heuristic itself. I also have a parent variable property here so that we can build the path via the A-star algorithm once we figure it out. The total cost methods are here as well that add together the g and h values, and a couple equals hash code and unique value methods here for dealing with the data structures internally. Within the actual A-star compute path method, initially I was trying to use a tree map to store the nodes in priority order, as well as being able to quickly look up the object using a key. But I quickly learned looking at the tree map implementation, if you have a comparator here, you can't order things differently if you have different nodes of different weights. So I found that it was easier to use a priority queue, which I can create my own comparator for, and that comparator is using the total estimated distance of the A-star node, and then just use a secondary map here that holds as the key is the unique location for the node, and then the node itself. That way I could quickly use contains methods to see if the node was in the frontier map, and I can also use the priority queue to get the latest. From here, it's a pretty standard A-star implementation where we take the starting node, we add it to the frontier, and then we loop through the frontier collection until it's empty. We remove the first node from the frontier. In this case is the one with the lowest cost node. We do a end check to see if we've reached our end goal. If we have, we build the path using the nodes. Otherwise, we mark that node as explored that we currently have. From here, we have a method that gets all of the neighboring nodes so that we know where all the possible locations are for the next step forward. In this method here, we're determining if these locations are valid, so we're checking up, down, left, right of the current square since we can't move in diagonals, and then we're also checking to see if the square that we're checking has something in the way, or if it's an open square that we can actually walk on. When these nodes are being created, we're also using a heuristic function here, which is the Manhattan distance, this to use as the h value. Once we have all possible locations that we can move to from the current node, we then check if the current node is either in the frontier or the explored list. If it's not, we can add it to the frontier, which is this check here. If we have seen this node before and it is in the frontier map, then we will check to see if the estimated cost is greater than the one that we currently have available or less than the one we currently have available. If it is, we replace the existing node with the one that we've just found so that we can have a better path through via the A-star algorithm.